in this lecture we'll answer two questions. In the first question, we'll find out the area of this green triangle, triangle ABC. And in the second question, we'll find out the length of this line segment AP that is equals to x. We have to find out the value of x. So we'll start with the first question. In the drawing, we have quadrangle AQABCP. We know that AQ equals to AC, and therefore triangle ACQ is an associated triangle, and QC is the base of the associated triangle, triangle QAC. In addition, we know that this is angle QPC that is equals to 60 degrees in size. This is angle PQC that is right angle. This is angle ABC that is also equals to 60 degrees in size. This is line segment AB or side AB that is equal to 5 units in its length. And this is line segment PC that is equals to 4 units in its length. Again, our task is to find out the area of this red triangle, triangle ABC. So first of all, we will do a construction. That is to say, from point A, we will draw perpendicular on the base QC of the associated triangle, triangle ACQ. Again, triangle ACQ is an associated triangle because AQ equals to AC. QC is the base of triangle, the associated triangle, triangle ACQ. So from the vertex A, we will draw perpendicular on the base BC. Again, from the vertex A, we will draw perpendicular on the base QC of the associated triangle, triangle ACQ. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and the base QC. This point is point M. So here we have rule 22. I'll repeat quickly on rule 22. According to rule 22, the perpendicular to the base of an associated triangle bisect the base. In the drawing, we have triangle ABC. This is an associated triangle because side AB equals to side AC. BC is the base of the associated triangle, triangle ABC. From the vertex A, we draw perpendicular AM to the base BC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and the base BC. This point is point M. According to this rule, rule 22, the perpendicular AM to the base BC of the associated triangle, triangle ABC bisect the base BC. That is to say, the perpendicular AM divides the base BC into two halves. The first half is BM and the second half is MC. And of course, BM equals to MC. So we can actually implement rule 22 in our drawing. Why? Because in our drawing, we have the associated triangle, triangle AQC, and we draw perpendicular AM to the base QC. According to rule 22, the perpendicular AM bisects the base QC. That is to say, it divides the base QC into two halves. The first half is QM, and the second half is MC. And of course, the first half QM is equals to the second half MC. So if we define the length of the first half QM as A, then the length of the second half MC must be also equal to A because they are equal to each other. In the next step, we will extend the perpendicular AM by a straight line until it touches line segment PC. I'll repeat again. We will extend the perpendicular AM by a straight line until it touches line segment PC. we will define the touching point of the extended perpendicular AM with line segment PC. This point is point N. AM is a perpendicular, it is absolutely a straight line. So if we focus on the right side of the straight line, AM is a perpendicular, is a straight line, and we extended the straight line AM by straight line. When you extend the straight line by straight line, the result must be a straight line. So AN is also a straight line. So if you focus on the right side of the straight line AN, at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles from one side of a straight line is equal to 180 degrees. So which angles we have at the right side of the straight line AN at point M? We have this angle that is a right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So we have the big right angle PQC. In the big right angle PQC, 90 degrees plus 60 degrees is 150 degrees. So 150 degrees plus this missing angle, this third missing angle, in total must be equal to 180 degrees. According to the rule that says that the sum of the angles from one in any triangle is equal to 180 degrees. Therefore, this third missing angle must be equal to 30 degrees in its size. Repeat again, according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the small right triangle MNC, 90 degrees plus 30 degrees is 120 degrees. So this third missing angle must be equal to 60 degrees in its size, according to the same rule that says that the sum of the angles on one side of a straight line, the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see that the big right triangle PQC is similar to the small right triangle NMC. So I will explain anyway why the big right triangle PQC is similar to the small right triangle NMC according to angle similarity rule. First of all, this is angle C, it is equals to 30 degrees in its size. Angle C is a common angle that belongs to both triangles. So I can write down that angle C equals to itself is a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 60 degrees and therefore they are equal to each other. So if you found out that all the figures of the big right triangle PQC are correspondingly equal to all the figures of this small right triangle NMC. And therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. If you found out that the big right triangle PQC is similar, this is the sign of similar, to the small right triangle MNC. According to angle similarity rule. And from the fact that the big right triangle PQC is similar to the small right triangle NMC, we will derive that the following relationship exists between their sides. We will derive that side NC of the small right triangle NMC over side PC of the big right triangle PQC is equal to side MC of the small right triangle NMC over side QC of the big right triangle PQC. But again, from the fact that the big right triangle PQC is similar to the small right triangle NMC, we derive that the following relationship exists between their sides. we will derive that side NC of the small right triangle MNC over side PC of the big right triangle PQC is equal to side MC of the small right triangle MNC over side QC of the big right triangle PQC. NC is the missing side, so we leave it as it is, over PC. PC equals to 4 units in its length, according to what is given as the question. And it is equal to MC. MC equals to A units in its length, according to our definition, over QC. QC equals to A plus A, that is 2A. So in total, we actually found out that NC over 4 equals to A over 2A. Here we have A in the numerator and A in the denominator, so A will get cancelled. So here we left, this time of the question, we left only with 1/2. That is equal to NC, is equals to NC over 4. So NC over 4 equals to 1/2. Here we will multiply this equation by 4 and finally we get that the missing side NC is equal to 4 over 2, that is 2. So we shall find out that this is the missing side NC that is equal to 2 units in its length. In the next step, I'll copy the big triangle NAB in the new page and we will analyze this big triangle NAB. Side AB equals to 5 units in its length, according to what is given as the question. Angle ABC equals to 60 degrees, according also to what is given as the question. And we already found out that angle NAB is also equals to 60 degrees in its size. So in this triangle A and B, 60 degrees plus 60 degrees is 120 degrees. So 120 degrees plus the size of this missing angle, in total they must be equal to 180 degrees, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Therefore, this third missing angle must be equal to 60 degrees in its size. So we found out that triangle A and B is an equilateral triangle. So I write it down. Triangle A and B is an equilateral triangle. This is to say, all of its angles are equal to each other, and all of its sides also equal to each other. If side AB equals to 5 units in its length, side AN must be also equal to 5, and side NB must be also equal to 5 units in its length. So NB equals to 5 units in its length. What is the length of this missing 97 side CB? From the drawing it is very easy to see that CB in total equals to NB minus NC. Again, CB equals to NB minus NC. So I write it down. CB equals to NB minus NC. So CB in total equals to NB is 5 minus NC is 2. So total CB equals to 5 minus 2, that is 3. CB equals to 3 units in its length. This is the missing side CB, that is equals to 3 units in its length. In the next step, we will do another construction, that is to say, from point A, we will do perpendicular on CB. Again, from point A, we will do perpendicular on CB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point A in CB. This point is point O. By doing this construction, we can edit the right green triangle, triangle AOB. We define the length of side AO as H. So in the next step, I'll copy the green right triangle AOB in a new page, and we find out the length of side AO that is equals to H. Okay, so the triangle AOB, the right triangle AOB. AB is the hypotenuse that is equals to 5 units in its length. AO, side AO equals to 8 units in its length, according to our definition. Angle ABO equals to 60 degrees in its size, according to what is given as the question. So actually, this is the right green triangle AOB that is coming from the original drawing. This right triangle AOB, sinus 60 degrees, equals to AO over AB. So sinus 60 degrees equals to AO, that is H, over AB, that is 5. So in total, we actually found out that sinus 60 degrees equals to H over 5. Here we will multiply this equation by 5, and finally we get that H equals to 5 times sinus 60 degrees. Sinus 60 degrees is equal to square root of 3 over 2. So in total, H equals to 5 times square root of 3 over 2. Okay, again, we should find out that H equals to 5 times square root of 3 over 2 units in its length. Our task is to find out the area of this green triangle, triangle ABC. So what is the area of the green triangle, triangle ABC? We know that the area of any triangle equals to the base of the triangle times the height over 2. We'll choose the base of this green triangle ABC as CB. So it will be equal to CB, the base CB, times the height is H. Why? Because it creates 90 degrees with the base CB. So the height is H over 2. So in total, the area of triangle ABC equals to CB times H over 2. CB is equals to 3 units in its length. We just right now found out that H equals to 5 times square root of 3 over 2, and we have to divide the expression by 2. So in the numerator in total we have 3 times 5, that is 15, times square root of 3 over 2 times 2, that is 4. So if you found out that the area of this triangle ABC, that is the area that we are looking for in this question, it is equals to either 15 times square root of 3 over 4 square units in its size, or in terms of numbers, the area of this main triangle ABC is equal to 6.5 square units in its size. So we finished with the first question. In the next step, I will present to you the second question, and we'll solve the second question of this lecture. In the second question, our task is to find out the length of this short line segment AP that is equals to x. We have to find out the value of x. So in the drawing we have a semicircle. Point O is the center of this semicircle. This is line segment PO that is equals to 10 units in its length. This is line segment QP that is equal to 21 units in its length. This is chord QS that is equals to 16 units in its length, and this is angle SQP that is a right angle. Again, our task is to find out the length of this short line segment AP that is equal to x. We have to find out the value of x. So first of all, we will complete the semicircle to a circle. And we will extend line segment QP by side line until it touches the circle. And we will define the touching point of the extended line segment QP with this circle. This point is point M. In the next step, we will join points S and M together by a straight line. So by doing this construction, we can do peripheral MQS. This is peripheral MQS that is equals to 90 degrees in size, and peripheral MQS subtend on chord MS. Again, peripheral MQS that is a right angle subtend on chord MS. So here we can implement rule 5. We'll repeat quickly rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees must subtend on the diameter of the circle. So in the drawing we have a circle. This is peripheral angle MAN, that is a right angle, and therefore, because of the fact that peripheral angle MAN is equal to 90 degrees in size, peripheral angle MAN must subtend on the diameter of this circle. And indeed, peripheral angle MAN subtend on MN, that is the diameter of this circle. So according to this rule 5, any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the circle. We can implement rule 5 in our drawing. Why? Because in our drawing we have here peripheral angle MQS, that is a right angle, and therefore according to rule 5, peripheral angle MQS must subtend on the diameter of this circle. Peripheral angle MQS subtend on chord MS, and therefore according to rule 5, according to rule 5, chord MS must be the diameter of this circle. So now if you found out that chord MS is the diameter of this circle according to rule 5. So point O is the center of the circle, point S is the point on the circle itself, therefore OS is the radius of this circle. We will define the radius of this circle as R, therefore OS is the radius of this circle, that is equals to R. Likewise, OM is also the radius of this circle, and therefore it is equals to R units in its length. In the next step, we will do another construction, that is to say from point O, that is the center of this circle, we will do perpendicular on QP. Again, from point O, we will do perpendicular on QP. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and QP. This point is point N. In the next step, we will focus on the big right angle, triangle SQM. We define this angle as alpha. So in the big right triangle SQM, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the small right triangle ONM, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. It is very easy to see that the big right triangle SQM is similar to the small right triangle ONM according to angle similarity rule. I will explain anyway why the big right triangle SQM is similar to the small right triangle ONM. First of all, this is angle M or alpha. That is a common angle that belongs to both triangles. Angle alpha belongs to the small right triangle M and O, and the angle alpha belongs, of course, to the big right triangle MQS. So angle alpha is a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees on the solve, and therefore they are equal to each other. So if you found out that all the triangles of the big right triangle SQM are correspondingly equal to all the triangles of this small right triangle ONM, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. We actually found out that the big right triangle SQM is similar. This is the side of similar to the small right triangle ONM. According to angle similarity rule. And for the fact that the big right triangle SQM is similar to the small right triangle ONM, we will derive that the following relationship exists between their sides. We will derive that side ON of the small right triangle ONM over side SQ of the big right triangle SQM is equal to side OM of the small right triangle ONM over side SM of the big right triangle SQM. Repeat again, from the fact that the big right triangle SQM is similar to the small right triangle ONM, we will derive that the following relationship exists between their sides. We will derive that side ON of the small right triangle ONM over side SQ of the big right triangle SQM is equal to side OM of the small right triangle ONM over side SM of the big right triangle SQM. ON is the missing side, so we leave it as it is. So it is actually ON over SQ. SQ equals to 6 units in its length, according to what is given as the question. And it is equals to OM. OM is the radius of this circle, that's equals to R according to our definition, over MS. MS is the diameter of this circle, that's equals to R. So in total, we should find out that ON over 16 equals to R over 2R. In this side of the equation, we have R in the numerator and R in the denominator, so R will get cancelled. So in this side of the equation, we left only with 1/2, that is equal to ON over 16. Or ON over 16 equals to 1/2. Here we will multiply this equation by 16, and finally here that ON equals to 16 over 2, that is 8. So if you found out that the missing side ON is equal to 8 units in its length. This is the missing side ON that is equal to 8 units in its length. In the next step, we will implement the Pythagoras theorem in the small right triangle ONP. And again, let's implement the Pythagoras theorem on this green small right triangle ONP. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is a progression for Pythagoras theorem. So actually, this is the small green right triangle ONP that is going to the domain, and this small triangle ONP goes into the Pythagoras theorem. PO squared, that is the square of the hypotenuse, is equal to NP squared plus NO squared. And again, PO squared, that is the square of the hypotenuse, equals to NP squared plus NO squared. PO is 10, therefore PO squared is 10 squared, it is 100. And it is equals to NP squared. NP is the missing side, so we leave it as it is, so it is NP squared plus NO squared. NO is 8, therefore NO squared is 8 squared, that is 64. So total we found out that 100 equals to NP squared plus 64. Here we subtract 64 from this equation, and finally we get that NP squared equals to 100 minus 64 is 36. So here we take a root out of this equation, and finally we get that NP, the missing side NP, is equal to the square root of 36, that is 6. So NP equals to 6 units in its length. So actually, this is the missing side NP, that is equals to, this is the missing side NP, that is equals to 6 units in its length. What is the length of this missing side QN? QN equals to QP minus NP. So I write it down. QN equals to QP minus NP. So QN equals to QP, that is 21, minus NP. We just right now found out that NP equals to 6. So in total QN equals to 21 minus 6, that is 15. QN equals to 15 units in its length. So actually, this is the missing side QN, that is equals to 15 units in its length. In the next step, we join points O and Q together by a straight line. Point O is the center of this circle, point Q is the point of the circle itself, therefore OQ is the radius of this circle. We define the radius of this circle as R, so OQ equals to R, is the radius of the circle. In the next step, I'll copy the right triangle O and Q on a new page, and we will implement the Pythagoras theorem on this right triangle O and Q. So here, this is the right triangle Q and O that are going from the original domain. The hypotenuse QO is also the radius of the circle that is equals to R. We already found out that Qn equals to 15 units in itself and side NO equals to 8 units in itself. So in this right triangle QNO, here by PT is the relation for Pythagoras theorem. According to the Pythagoras theorem, this right triangle QNO, QO squared, that is the square of the hypotenuse, is equal to Qn squared plus NO squared. QO is R, therefore QO squared is R squared, and it is equals to Qn squared. Qn is 15, therefore Qn squared is 15 squared, that is 225 plus NO squared. NO is 8, therefore NO squared is 8 squared, that is 64. So in total we actually found out that R squared equals to 225 plus 64. So 225 plus 64 equals to 289. So in total we actually found out that R squared equals to 289. Here we take out of this equation and finally get that R equals to the square root of 289, that is 17. So the radius of this circle is equal to 17 units in its length. The radius R of this circle is equal to 17 units in its length. Okay, so R equals to 17 units in its length. OA is also the radius of this circle. So the radius R equals to 17, and OA is also the radius of the circle that equals to 17 from one side, but from the other side, OA equals to AP plus PO. OA equals to AP plus PO. So OA equals to AP, AP is X, plus PO. PO equals to 10 units in its length. And from this long equation, R equals to 17 equals to OA equals to AP plus PO equals to X plus 10. We will derive that 17 equals to X plus 10. Okay, 17 equals to X plus 10. So here we subtract 10 from this equation and we get that X equals to 17 minus 10, that is 7. So AP, that is equals to X, is equals to 7 units in its length. So the answer to the question is that the length of this line segment AP, that is equals to X, is equals to 7 units in its length. Okay. So finish with the second question. In the next step, I summarize the lecture. We'll start with the first question, of course. Our task in the first question is to find out the area of this green triangle, triangle ABC. So, in the drawing, we have quadrilateral QABCP, and we know that AQ equals to AC, and therefore triangle AQC is an associated triangle, and QC is the base of this associated triangle, triangle AQC. In addition, we know that this is angle QPC, that's equals to 60 degrees inside. This is angle PQC, that is right angle. This is line segment PC, that is equals to 4 units in its length. This is angle ABC, that is equals to 16 degrees in its size. And this is side AB, that is equals to 5 units in its length. Again, our task is to find out the area of this green triangle, triangle ABC. So in the first step, we did the construction, that is to say, from point A, we draw perpendicular on QC. Again, from point A, we draw perpendicular on the base QC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and the base QC, this point is point M. So here, we can implement rule 22. According to rule 22, the perpendicular to the base of an associated triangle bisects the base. Again, according to rule 22, the perpendicular to the base of an associated triangle bisects the base. So triangle AQC is an associated triangle and QC is the base. According to rule 22, the perpendicular AM bisects the perpendicular AM to the base QC of the associated triangle, triangle AQC, bisects the base QC. That is to say, it divides the base QC into two halves. The first half is QM and the second half is MC. And of course, the first half QM must be equal to the second half MC. So if we define the length of the first half QM as A, then the length of the second half MC must be also equal to A, because they are equal to each other. In the next step, we extended the perpendicular AM by a straight line until it touches line segment PC. We define the touching point of the extended perpendicular AM if line segment PC, this point is point M. AM is a perpendicular, it is absolutely a straight line. When you extend the straight line AM by a straight line, the result AN must be also a straight line. When you extend the straight line by straight line, the result must be a straight line. So AN must be also a straight line. So if we focus on the right side of the straight line AN at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the right side of the straight line AN at point M? You have this angle that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. Okay? So this missing angle must be equal to 90 degrees in its size. So in the right triangle QPC, 90 degrees plus 60 degrees is 150 degrees. 150 degrees plus the size of this missing angle, in total must be equal to 180 degrees, according to the rule that the sum of the angles in the triangle is equal to 180 degrees. Therefore, this third missing angle must be equal to 30 degrees in its size. Likewise, in the small right triangle M and C, 90 degrees plus 30 degrees is 120 degrees. So 120 degrees plus the size of this third missing angle, in total must be equal to 180 degrees according to the sum rule, that the sum of the angles in the triangle is equal to 180 degrees. Therefore, this front missing angle must be equal to 60 degrees in size. So actually it is very easy to see that the big right triangle QPC is similar to the small right triangle MNC according to angle similarity rule. I'll explain anyway why the big triangle QPC is similar to the right triangle MNC. First of all, this is angle C. This is equals to 30 degrees in size. So you can write down that angle C equals to itself is a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 60 degrees and therefore they are equal to each other. So if you found out that all the figures of the big right triangle PQC are corresponding equal to all the figures of the small right triangle NMC. And therefore, those two right triangles are similar to each other according to angle similarity rule. So, here, the big triangle PQC is similar to the small right triangle NMC according to angle similarity rule. And from the fact that the big right triangle QPC is similar to the small right triangle MNC, we will derive that the following relationship exists between their sides. We will derive that side NC of the small right triangle NMC over side PC of the big right triangle PQC is equals to side MC of the small right triangle NMC over side QC of the big right triangle PQC. And again, from the fact that the big right triangle PQC is similar to the small right triangle NMC, we derive that the following relationship exists between their sides. We will derive that side NC of the small right triangle NMC over side PC of the big right triangle PQC is equals to side MC of the small right triangle NMC over side QC of the big right triangle PQC. NC is the missing side, so we leave it as it is, over PC. PC equals to 4 units in its length, and it is equals to MC. MC is A over QC. QC is A plus A, that is 2A. So in total, we found out that NC over 4 equals to A over 2A. And again, NC over 4 equals to A over 2A. Here we have A in the numerator and A in the denominator, so A will get cancelled. And here we left in this side of the equation only with 1 half. So 1 half equals to NC over 4. NC over 4 equals to 1 half. Here we multiply this equation by 4 and finally found out that NC equals to 4 over 2, that is 2. So this is the missing side NC, that is equals to 2 units in its length. In the next step, I copied the big triangle A and B in a new page. We analyze this big triangle A and B. This is the big triangle A and B that is coming from the original drawing. This big triangle A and B, AB equals to 5 units in its length, according to what is given as the question. This is angle ABM that is equal to 60 degrees in size, and this is angle ANB that is also equal to 60 degrees in size. So 60 degrees plus 60 degrees is 120 degrees. So 120 degrees plus the size of this missing angle, in total it must be equal to 180 degrees, according to the rule that said that the sum of the angles in any triangle is equal to 180 degrees. Therefore, this third missing angle must be equal to 60 degrees in its size. So if you found out that this is the big triangle A and B, that is an equilateral triangle. And in any equilateral triangle, all the sides are equal to each other. AB equals to 5, therefore AN must be also equal to 5, and B must be also equal to 5 units in its length. Okay. So NB equals to 5 units in its length, and equals to 5 units in its length. So what is the length of side CB? CB equals to NB minus NC. Okay, CB equals to NB minus NC. It again, CB equals to NB minus NC. CB equals to NB minus NC. So CB equals to NB, that is 5, minus NC, that is 2. So in total, CB equals to 5 minus 2, that is 3. CB equals to 3 units in its length. In the next step, we did the construction, which is to say from point A, we drop a believer on CB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and CB. This point is point O. In the next step, we copy the right hand triangle A or B in a new page, and we found out the length of the missing side AO that is equals to H. So actually, this is the right grand triangle AOB that I copy from the original domain. In this grand triangle AOB, sine of 60 degrees equals to AO over AB. Again, sine of 60 degrees equals to AO over AB. So sine of 60 degrees equals to AO, that is H, over AB, that is 5. So in total, sine of 60 degrees equals to H over 5. Sine of 60 degrees equals to H over 5. Here, we multiply this equation by 5 and found out that H equals to 5 times sine of 60 degrees. Sine of 60 degrees is equal to 3 over 2. So H equals to 5 times equal to 3 over 2. Our task is to find out the area of this triangle, the grand triangle ABC. You know that the area of any triangle equals to the base of the triangle times the height over 2. We will choose the base of this grand triangle ABC is CB. So the base is CB times the height is H. Why the height is H? Because it creates 90 degrees with the base CB. Divided by 2. So in total, we found out that the area of the grand triangle ABC equals to the base CB times the height H over 2. CB equals to 3 times H, that is 5 times equal to 3 over 2, divided by 2. So in total, in the numerator we have 3 times 5, that is 15, times equal to 3, over 2 times 2, that is 4. So in total, we found out that the area of this right triangle ABC is equal to either 15 times equal to 3 over 4 square units in its size. In terms of numbers, the area of this grand triangle ABC is equal to 6.5 square units in its size. So we finish with the first question. In the next step, I present it with the second question and we solve the second question of this lecture. In the second question, our task is to find out the length of this line, short line segment AP that is equals to x. We have to find out the value of x. So in the drawing we have a semicircle. Point O is the center of this semicircle. We also know that line segment PO equals to 10 units in its length. Line segment QP equals to 21 units in its length. This is called QS, that is equal to 16 units in its length. This is angle QPC, that is right angle. Again, our task is to find out the length of this short line segment AP that is equal to x. We have to find out the value of x. So first of all, we completed this semicircle to a circle, and we extended line segment QP by straight line until it touches the circle at this point, point M. And we define the touching point of the extended line segment QP with the circle, this point is point M. In the next step, we join points S and M together by straight line. By doing this from this construction, we get the diff, peripheral angle SQM. Peripheral angle SQM is a right angle, it is equal to 90 degrees in its size according to what is given as the question. And peripheral angle SQM subtend on chord SM. Again, peripheral angle SQM subtend on chord SM. And according to rule 5, any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the circle. So peripheral angle SQM is equal to 90 degrees in its size. Therefore, peripheral angle SQM must subtend on the diameter of this circle. Peripheral angle SQM subtend on SM, and therefore SM must be the diameter of this circle. Again, SM is the diameter of this circle according to rule 5. Point O is the center of this circle. Point S is the point on the circle itself. Therefore, OS is the radius of this circle that is equals to R. Likewise, OM is also the radius of this circle that is equals to R. In the next step, we did the construction. Let's just to say from point O, we go perpendicular on PQ. Again, from point O, we go perpendicular on PQ. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and QP. This point is point N. So here we have the big right triangle QPM. If you focus on the big right triangle SQM, we define this angle as alpha. So this angle equals to alpha. This angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the small right triangle O and M, this angle equals to alpha. This angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. So actually it is very easy to see that the big right triangle SQM is similar to the small right triangle, triangle O and M, according to angle, similarly to rule. I will explain anyway why the big right triangle SQM is similar to the small right triangle, triangle O and M. First of all, this is angle alpha, that is a common angle that belongs to both triangles. So we can write down that angle alpha equals to itself is a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So I can prove that all the figures of the big right triangle SQM are correspondingly equal to all the figures of the small right triangle O and M, and therefore those two right triangles are similar to each other according to angle similarity rule. So if again, we found out that the big right triangle SQM is similar to the small right triangle O and M according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side NO of the small right triangle O and M over side QS of the big right triangle QSM is equal to side MO of the small right triangle NOM over side MS of the big right triangle QSM. Because again, from the fact that the big right triangle SQM is similar to the small right triangle NM, we derive that the following relationship exists between their sides. We derive that side ON of the small right triangle ONM over side SQ of the big right triangle SQM is equal to side OM of the small right triangle ONM over side SM of the big right triangle SQM. ON is the missing side, so we leave it as it is, over QS. QS equals to 16 units in itself, and it is equals to OM. OM is the radius of this circle, that is equals to R over SM. SM is the diameter of this circle, that is equals to 2R. So in total, we found out that ON over SQ equals to ON over 16 equals to R over 2R. Here we have R in the numerator and R in the denominator, so R will get cancelled. So in this side of the equation, we left only with 1/2, that is equals to ON over 16. So ON over 16 equals to 1/2. Here we multiply this equation by 16 and find out that ON equals to 16 over 2, that is 8. So ON equals to 8 units in itself. This is the missing side ON that is equals to 8 units in its length. In the next step, we implemented the Pythagoras theorem on this small right again triangle NOP. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually, this is the right triangle NOP, with the correct of the original domain. In this right triangle NOP, PO squared, that is the square of the hypotenuse, equals to PN squared plus ON squared. PO is 10, therefore PO squared is 10 squared, that is 100, and it equals to NP squared. NP is the missing side, so we leave it as it is. So it is NP squared plus ON squared. ON is 8, therefore ON squared is 8 squared, that is 64. So in total, we found out that 100 equals to NP squared plus 64. Here, subtracted 64 for this equation, we found out that NP squared equals to 100 minus 64, that is 36. So NP squared equals to 36. Here we took a root out of this equation and we found out that NP equals to the square root of 36, that is 6. So we found out the missing side NP is equals to 6 units in its length. What is the length of the missing line segment QN? From the drawing, it is very easy to see that QN in total equals to QP minus NP. Again, QP minus NP equals to QN. And again, QN equals to QP minus NP. So QN equals to QP, that is 21 according to what is given as the equation, minus NP. We just found out that NP equals to 6. So in total, QN equals to 21 minus 6, that is 15. So QN equals to 15 units in its length. This is the missing line segment QN, that is equals to 15 units in its length. In the next step, we join points O and Q together by straight line. Point O is the center of this circle, point Q is the point of the circle itself, therefore OQ is the radius of this circle, and this equals to R. So in the next step, I'll complete the right triangle Q and O in the new page, and we implemented the Pythagoras theorem on this right triangle, triangle Q and O. So actually, this is the right triangle Q and O, this is the correct from the original domain. This right triangle Q and O. Q all square, that is the square of the hypotenuse, equals to Qn square plus NO square. Again, Q all square, that is the square of the hypotenuse, equals to Qn square plus ON square. QO is R, therefore Q all square is R square, and it is equals to Qn square. Qn is 15, therefore Qn square is 15 square, that is 225, plus ON square. ON is 8, therefore ON square is 8 square, that is 64. So in total, we found out that R square equals to 225 plus 64. 225 plus 64 is 289. So R square equals to 289. Here we took a root out of this equation and we found out that R equals to the square root of 289, that is 17. So we found out that the radius of this circle R is equal to 17 units. And OA is also the radius of this circle, and therefore it is also equals to 17 units in its length. So R equals to 17 equals to OA. From one side, OA is the radius of the circle, is equals to 17 units in its length. From the other side, OA or AO also equals to AP plus PO. Again, AO equals to AP plus PO. So you can write down that AO equals to AP plus PO. AP is the line segment that we're looking for in this question, and it is equals to X. So AP equals to X, and PO equals to 10. PO equals to 10 units in itself, according to what is given us in the question. So PO equals to 10. And from this long equation, R equals to 17 equals to OA equals to AP plus PO equals to X plus 10. We derive that 17 equals to X plus 10. 17 equals to X plus 10. If we subtract the 10 from this equation, and finally found out that OA equals to, X equals to 17 minus 10, that is 7. So actually, line segment AP that equals to X is equal to 7 units in its length. So the answer to the question is that the length of the short line segment AP that is equals to X is equal to 7 units. Okay, thank you very much.